Hey guys, this video is about properties of acids and bases. So the Arrhenius definition of acids and bases is this. Well, let me start out with this. There are several different definitions, and we're going to go through them in order from the oldest to the more modern. And as we go through, the more modern definitions encompass the older definitions but extend them further. So this is the oldest of the ones we're talking about, Arrhenius definition. And the definition of an Arrhenius acid is a compound that produces the hydrogen ion in water. So for example, if we put hydrochloric acid in water, we produce the hydrogen ion, thus it's an Arrhenius acid and chloride ion. And an Arrhenius base is something when you put it into water, produces the hydroxide ion. A real common example of this would be any metal hydroxide, sodium hydroxide, potassium hydroxide. Those are all soluble, so when you put them in water, we get the just hydroxide ion from the hydroxide. But here's another example of something that does not start out with the hydroxide, at least not obviously. Ammonia. We put ammonia in water. It ends up that ammonia reacts with water to produce the hydroxide ion, thus it's an Arrhenius base, and also the ammonium ion. So that's one definition. The next more modern definition would be the Bronsted-Lowry definition. Now, a Bronsted acid is something that's a proton donor. Now, the key difference here is there's no water involved. In the Arrhenius definition, we had to have an aqueous solution and we had to produce the hydrogen ion for it to be an acid. Here, it's just something that donates a proton, so it encompasses solutions that are not necessarily aqueous, as well as aqueous solution. So, for example, here, in the dihydrogen phosphate, when we put it into water, the dihydrogen phosphate donates one of these protons, a hydrogen with a plus charge, onto the water. The water molecule accepts that proton, and we end up with the hydronium ion. This H3O plus, guys, this is called the hydronium ion, and the hydrogen phosphate or biphosphate. Now, we're going to see this H3O plus, the hydronium ion, popping up quite a bit when we talk about acids and bases. And the only important thing for us is to remember that this is just another way at this point of writing a proton, H+. It's just that in water, when there's H+, a lot of times it forms hydronium. Now, Bronsted bases are proton acceptors. So, for example, if we put the sulfate ion into water, what happens is the sulfate accepts a proton from water, forming hydrogen sulfate. And so it's accepting a proton, it's being a base. And notice that water is donating a proton, so water is being an acid in the Bronsted-Lowry sense, just as water is being a base up here. Now, something that's amphoteric, speaking of amphoteric species, is something that can act as either an acid or a base depending upon the conditions, right? So an example of this would be biphosphate or hydrogen phosphate. Under some conditions, when you put that in water, the hydrogen phosphate donates a proton to water, forming the hydronium ion. So it donated a proton, it's a Bronsted-Lowry acid, and leaving the phosphate ion also. Under different conditions, same exact compound, put hydrogen phosphate into water, it can accept a proton from water, forming the dihydrogen phosphate. So it accepted a proton, it's acting as a Bronsted-Lowry base, and notice here water is acting as a Bronsted-Lowry acid, and we form hydroxide. Now, the next, the more modern definition, most modern definition of these three is the Lewis definition of acids and bases. Now, real quick, we're going to use this every now and then in here. It encompasses everything we talked about, plus it includes compounds that would not be included on our previous definitions. But in this, to be honest, in this course right here, general chemistry, we don't use it that much. We do use it every now and then. Now, having said that, when you guys get into OChem, organic chemistry, this you use quite a bit. So, here are the definitions. A Lewis acid is an electron pair acceptor, and a Lewis base is an electron pair donor. Now, there's a lot of definitions here and a lot of stuff going on. So, what I do, just a little trick, maybe if it helps for me, what makes it easy to remember this is I kind of focus on the one that we most commonly use in this course, Bronsted-Lowry. Acid is a proton donor, base, proton acceptor. And then I think about the Lewis definition as being kind of the opposite of everything. So an acid, okay, instead of being a proton donor, is an electron pair acceptor. So accepting is the opposite of donating, and to me an electron pair is kind of the opposite of a proton in terms of electrical charges. And likewise, in the Bronsted-Lowry definition of a base, it's a proton acceptor. In the Lewis definition, it's a electron pair donor. So so here, let's look at this reaction down here. This is showing ammonia reacting with trifluoroborane, okay, in a Lewis base acid-base reaction. So what's happening here is this lone pair of electrons is moving over here onto the boron, forming a bond. So the boron's accepting an electron pair. So that means this reaction, the trifluoroborane, is a Lewis acid. No protons, no water, nothing, right? And the ammonia donating a pair of electrons is a Lewis base, right? And when a Lewis base reaction happens, a lot of times we form what's called a coordinate covalent bond. So what's happening over here is these electrons here formed a single covalent bond between the nitrogen and the boron. Now, a coordinate covalent bond is just a regular old covalent bond as opposed to an ionic bond. But the only difference between a coordinate covalent bond and a regular covalent bond is where the electrons came from. So in this case, both of these electrons originated on the nitrogen atom that formed this bond here. That's a coordinate covalent bond. As in Chem 101, most of the covalent bonds we saw formed one electron from each atom. And that's not a coordinate covalent bond, it's just a regular covalent bond. And the other thing we get out of this, guys, is this notation here. Again, we use it every now and then in this course, but when you get to OChem, use it all the time. And it's these arrows, right? This arrow, this is the convention, this is what they show. The tail always starts at the electrons that are moving. It shows the movement of electrons. And the head of the arrow points to the atom where those electrons are going to end up. If it's a double-headed arrow like this, it indicates 2 electrons are moving. Single-headed arrow would mean that 1 electron is moving. Okay, so that's that notation. That's Lewis acids and bases. All right, so now let's talk about conjugate pairs. So conjugate acids and bases. So in this reaction right here, the hydrogen sulfate is reacting with water to form hydronium and sulfate. Okay, so hydrogen sulfate is donating a proton to water, so it's being an acid, Bronsted-Lowry acid. Water is accepting a proton as being a Bronsted-Lowry base. Now on the other side of the arrow, so this is in equilibrium, guys. This is going back and forth, right? So that means if we could see the atoms and the molecules in that solution, we'd see sometimes hydronium reacting with sulfate to produce hydrogen sulfate in water. So on the other side of the arrow, the conjugate acid of the base, so the base and its conjugate acid are related. Okay, so this is the base here, water. It accepted a proton, so after it accepted that proton, now it's a conjugate acid. Likewise, this is the acid, hydrogen sulfate. So after it loses its proton, after it donates its proton to water, what's left, what's on the other side of the arrows, is the conjugate base. So this is the acid, this is the conjugate base, this is the base, this is the conjugate acid. Now, a real quick trick to easily determine what the conjugate base or the conjugate acid of a compound is if you wanted to know the conjugate acid, all you do is add a proton. What that means is add an H to the formula and add a positive charge. So here, water has 2 hydrogens, 2 H's, no charge. When we add a hydrogen with a plus charge, we get 3 hydrogens and a positive 1 charge. Likewise, to form the conjugate base of an acid, we remove a hydrogen, remove a proton. So that means we remove an H, 1 less H over here in the formula, and we remove a positive charge. So this had a negative 1 charge. When we take another of the protons away, we have 1 less positive charge. Now we have an overall negative 2 charge here in the conjugate base. So having said that, why don't we do a little example? So the question is, guys, what's the conjugate base of ammonia, which is NH3? So when you get your answer, come on back. Welcome back, guys. So here's to do this. Amide, NH2 minus. So what we do is, to get the conjugate base, we remove a hydrogen, an H plus, we remove a hydrogen. So there's 2 hydrogens instead of 3. And this has a 0 charge. When we remove a positive 1 from that, there's 1 extra electron, and it has an overall negative 1 charge. So the amide ion is what that's called. conjugates. Now, what we're going to do, guys, is talk about the relationship between the structure of a molecule of an acid and its strength, how strong that acid is. When we say acid strength, guys, what we're talking about is how easily that acid donates a proton. So notice we're falling into the Bronsted-Lowry definition, which works pretty well for all this stuff. So how easy is it for that molecule to lose a proton, to donate a proton? Now we think about this in terms of structure. There's two things we have to consider. First, how easy it is to break the bond between the acidic proton, the proton that's leaving, and the rest of the molecule, number one here. And also, how stable the conjugate base of the acid is after we remove the acidic proton. So how stable the resulting anion is. So when we're looking at how easy it is to break the bond, there's two factors that come into play. How long the bond is. The longer a bond is, the easier it is to break. The polarity of the bond. So now the bond we're talking about is always, guys, always here in this scenario, the bond between the proton, hydrogen, and whatever atom it's attached to in the acid. So the longer that bond is, the easier it is to break, and the stronger the acid. The more polar that bond is, the easier it is to break. So if you think about it, the more polar it is, that means that the electrons are shifted more to the more electronegative atom and more away from the it's going to be the hydrogen that's less electronegative atom. And so basically what that's doing is it's starting to break the bond for you, so you don't have to put as much energy into complete the breaking that bond. And so think about difference in electronegativity. The greater the difference in electronegativity between the hydrogen atom and the atom it's attached to, the more polar that bond is, and the easier it is to break. Now, in terms of how stable the conjugate base is, if we end up with a monatomic anion, one of the factors that comes into play is the electronegativity. Well, pretty much the only factor there. The more electronegative an element is, as a monatomic, meaning single atom anion, the more stable it is, because more electronegative basically means it has a greater attraction for negative charge. It can stabilize that negative charge more easily than something that's less electronegative. Now, when we have more than one atom in the resulting anion, the conjugate base, we have a polyatomic anion, and there, delocalization of the charge becomes important. So when we say delocalization of the charge, I'll show you what that means in a second, guys, but think resonance forms. So the more delocalized the charge is, the more stable that anion is. And this is a fundamental principle of electrostatics, really. And that is that the greater a volume an electric charge is spread out over, the more stable that thing with the charge is, in this case the anion. All right, so let's use these and apply them. So first we'll look at the hydrohelic acids. That just means the acids that form with the halogens, fluorine, chlorine, bromine, and iodine. And so here, I'm just giving you guys, telling you straight up, this is the relative acidity. Hydrofluoric acid is a lot weaker than hydrochloric, hydrobromic, and hydroiodic. Hydrochloric is, so of these, the strongest is hydroiodic. Hydrofluoric, okay, so we're going to see later on, we have what we call strong acids and weak acids. You probably saw that in Chem 101. Hydrofluoric acid is a weak acid. The rest of these are strong acids. Now here, okay, even though fluorine, the fluoride ion, is more electronegative than chlorine, which is more electronegative than bromine, which is more electronegative than iodine, that's not, that effect in this scenario, in this case, is not as important as the bond lengths. So if we look at, so we know, the other thing we know about fluorine or the fluoride ion compared to bromide, chloride ion compared to bromide compared to iodide, is that they get bigger as we go up. So fluoride's a lot smaller than chloride, smaller than bromide, smaller than iodide. Now, because the only bond in these molecules, in these acids, guys, is the bond between the hydrogen and the fluorine, right? There's just one bond. The size of this bond, the length of this bond, which determines the strength of the acid, gets longer as we go up. Because on one side of that bond, there's a hydrogen atom, which is always the same size, pretty much. On the other side of the bond, though, the nucleus of that atom gets farther and farther away because the atom gets bigger and bigger and bigger. And so the bond between the hydrogen and fluorine might look something like this. By the way, this is not to scale. I just drew these by hand, right? This is the hydrogen-chlorine bond length, hydrogen-bromine, hydrogen-iodine. But you get the idea. As the bond gets longer, it gets easier to break, and that in this set of acids is what determines the most acidic and least acidic. This is the most acidic, this is the least acidic because this is the shortest bond, and this is the longest bond. So that's hydrohalic acids. Now let's look at oxoacids. What's an oxoacid? Well, it's all in the name, really. It's an acid that contains oxygen. Easy. Examples would be nitric acid, nitrous acid, sulfuric acid, sulfurous acid, perchloric, hypoiodous, a lot of them, right? You saw these at least, the very least, back when we did nomenclature in Chem 101. So now, comparing the relative strengths of oxoacids, guys. So if we have the same central atom in two different acids with different numbers of oxygen atoms, then the more oxygen atoms there are, the stronger that acid's going to be, because the resulting anion, the conjugate base, will be more stable, because the more oxygen atoms there are, the more resonance forms there are. On the other hand, if we have the same number of oxygen atoms, but different central atoms, then the compound that has the central atom that's more electronegative will be the stronger acid. Right? We'll look at both of these scenarios in just a minute. But so predicting relative strength. So nitric acid versus nitrous acid. So nitric acid is HNO3, so it has 3 oxygens. Nitrous acid is HNO2, has 2 oxygens. And we predict nitric acid to be stronger than nitrous acid because it has more oxygens. And it is. Now comparing nitric acid to sulfurous acid, both of these guys have 3 oxygens. But sulfur is less electronegative than nitrogen, the central atom, so we predict nitric acid, is the stronger acid, and it is. There's a few other things going on, but that's what we're looking at now. So let's look at the different numbers of oxygen atoms, comparing nitric acid to nitrous acid. So nitric acid has these 3 oxygens, so when nitric acid loses its proton, okay, it forms the nitrate ion. The nitrate ion has 3 resonance forms, and the resonance forms are double bond to one oxygen, to another, or to another. And real quick, trip back into Chem 101, guys. Remember, when you have resonance forms, that doesn't mean there are 3 different structures. It just means that the real one structure of that species is a resonance hybrid of those 3 resonance structures that we write. What that means for us is that if you calculate the formal charges here, there's a -1 here, and a -1 here, and a 0 here, and a +1 on the nitrogen. But these negative formal charges are distributed amongst the oxygens. Or another way of looking at it, without even formal charges, overall this has a -1 formal charge, not formal charge, a real charge. And that negative charge is spread out over these 3 oxygens. It's more delocalized than nitrous acid, where in nitrous acid the conjugate base is nitrite, NO2-. It only has 2 oxygen atoms, 2 resonance forms, and so that negative charge is only spread out over 2 oxygens, not as delocalized as nitrate, and so nitrate is more stable than nitrite, meaning nitric acid is a stronger acid because it's easier to form the more stable conjugate base. Now let's look at the central atom. So comparing nitric acid to sulfurous acid, HNO3 to H2SO3. So here, when we remove this acidic proton from nitric acid, as we saw, we have nitrate, 3 resonance forms. When we remove this proton from sulfurous acid, we have hydrogen sulfate, 3 resonance forms also. And there's something else going on here, but because nitrogen is more electronegative than sulfur, it does a couple of things for us, guys. First, over here in the acid form, because it's more electronegative than sulfur, it's pulling these electrons away in this bond from the hydrogen, polarizing this bond more, making it easier to break, and making this a stronger acid. Compared to this, where sulfur is less electronegative. It's not pulling the electrons as strongly. Over here, we have 3 resonance forms here, 3 resonance forms here, but that negative charge is spread out. It's pulled in towards the nitrogen more. It's delocalized a little bit more onto the nitrogen because nitrogen's more electronegative than sulfur. Now, the other thing that's going on here, which we're not going to deal with yet, is that one of these resonance forms in the hydrogen sulfate ion doesn't contribute as much as the others because if you calculate the formal charges with the double bond here to this oxygen with hydrogen on it, it's not as good. But that's a different lecture. All right, let's talk about carboxylic acids now. Carboxylic acids are organic acids, meaning they contain carbon, and they have this general form here, RCO2H. R just means it could be any combination of hydrogens and or carbons, and sometimes there's even some other elements in there, but it has to contain at least hydrogen or carbon. That's R, and then it's a carboxylic acid. So the CO2H is the carboxylic acid, what we call functional group. It's what makes it an acid. And so let's just look at two carboxylic acids, formic acid and acetic acid. Formic acid is secreted by ants when they bite you. And acetic acid, well, dilute acetic acid is vinegar. Or it's like if wine goes sour, it's because the ethanol is oxidized to acetic acid. Now, here in formic acid, there's our CO2H group, this right here. It's a carboxylic group. And R in this case is just hydrogen, still a carboxylic acid. In acetic acid, same idea here, guys, right? CO2H, there's the carboxylic group. The R here is CH3, and these are pretty simple carboxylic acids. These can get pretty long, the tails here. Real quick, kind of interesting. This is a little bit more than we've been talking about, but you guys can get it. It ends up that formic acid is about 10 times stronger than acetic acid. Right? Means it can donate its proton more easily. By the way, this is the acidic proton right here, and this is the acidic proton right here. In carboxylic acids, the acidic proton is always the hydrogen, the proton that's on one of the oxygens in the carboxylic functional group. But the reason it ends up that formic acid is so much stronger than acetic acid is that in acetic acid, this carbon right here is actually what we call electron donating. So instead of helping, so when we take this acidic proton off, instead of helping to delocalize the charge a little bit out here, it's actually doing the opposite. It's pushing electrons this way, localizing the charge, making it less stable. Plus, what it does is it actually pushes electrons up here in the acid form, making this oxygen-hydrogen bond less polar, harder to break compared to formic acid. Okay. So, question, guys. Example, which of these two carboxylic acids is stronger? This is acetic acid. This is fluoroacetic acid. You don't have to know these names yet. I'm just throwing them out there for you. And the only difference, if you notice, is in acetic acid, there's a hydrogen here, and fluoroacetic, that has been replaced with a fluorine. So when you think you have an answer, and why? So why is that one the stronger acid? Go on back. Welcome back, guys. So here we go. Fluoroacetic acid is the stronger acid. And the reason for that is fluorine is the most electronegative element in the periodic table. And what that means is, first, in the acid form, it's pulling electrons away from this oxygen-hydrogen bond, okay? Polarizing it, making it harder to break. Now it's a couple of bonds away, but it's still doing that. Also, in the conjugate base form, when you get the, it's called the carboxylate ion, the negative charge is spread out more. It's more delocalized because this fluorine is pulling those electrons towards it, helping delocalize that charge compared to just a hydrogen. So fluoroacetic acid is stronger than acetic acid. All right, moving on. The autoionization of water. So water actually is, you think it's simple, right? What, it's just water, right? But it's actually a really, really interesting and complicated molecule. If you just have a beaker of absolutely pure water, which by the way is very hard to get if you look closely enough, but let's say you did. It ends up the water molecules react with this themselves in an acid-base reaction. And what they do is two molecules of water bump into each other, right? If they have enough energy and the right orientation, one of those water molecules donates a proton to the other molecule. So one of these is acting as an acid, one is acting as a base, and we end up with the hydronium ion and hydroxide ion. Or another way of writing that is just a single molecule of water dissociating into hydrogen ion and hydroxide ion. These two are equivalent guys. So now the equilibrium constant for this process we call Kw, what W for water. If we write it this way, it's just equal to the concentration of hydronium times hydroxide. This way, hydrogen ion times hydroxide ion concentrations. The reason water doesn't appear is because water is in the liquid form, and that means that's a heterogeneous equilibrium and its concentration doesn't change, so we don't write it in the equilibrium expression. So at 25 degrees Celsius in pure water, the concentration of hydronium ion or hydrogen ion and hydroxide are the same. 1.0 times 10 to the minus 7th molar. Remember that. Which means that if we plug this up here or here, we see that the value for Kw at 25 Celsius pure water is 1.0 times 10 to the minus 14. Remember that number. Now, if it's at a different temperature than different temperature than 25 Celsius, Kw changes, right? And we'll see that in some of in the worksheets and some examples. And it's only really good to we might stretch it to 3 sig figs, but we're going to call it 2 sig figs here. Okay. All right, so having said that, aqueous solution. So now it's not pure water. So we have something else in the water that's affecting the hydrogen ion or hydronium ion and hydroxide ion concentrations. But even if it's not pure, Kw still holds. Kw is still equal to the same hydronium ion times hydroxide ion, or hydrogen ion concentration times hydroxide ion, and it's still at 25 Celsius equal to 1.0 times 10 to the minus 14th. So if the hydrogen ion and hydroxide ion, or hydronium ion and hydroxide ion, same thing, concentrations are the same, that's what we mean when we say a solution is neutral. At 25 Celsius, that means they're both going to be 1.0 times 10 to the minus 7th molar. Different temperatures, different concentrations. If the hydrogen ion concentration is greater than the hydroxide ion concentration, that's what we mean by an acidic solution. And if the hydrogen ion concentration is less than the hydroxide ion concentration, that's what we mean for that solution to be basic. All right, so let's do an example. Let's calculate the hydrogen ion or hydronium ion concentration in an aqueous solution at 25 Celsius. By the way, guys, if you're not given a temperature in this material and acid-base stuff, we always assume it's at 25 Celsius. If it's different, then it'll be like, we'll make a big deal about it. So anyway, what's the hydrogen ion concentration in this aqueous solution if the hydroxide ion concentration is 7.44 times 10 to the minus 5th molar? So we're just plugging into Kw basically. So once you guys get your answer in, come on back when you finish. Welcome back, guys. So we're using Kw because we're asked for hydrogen ion concentration. We just rearrange this a little bit and solve for hydrogen ion concentration. Kw over the concentration of hydroxide. Plug in 1.0 times 10 to the minus 14th for Kw, concentration of hydroxide here, and we get the concentration of hydrogen ion, 1.3 times 10 to the minus 10th molar. Notice the hydroxide ion concentration is greater than 1 times 10 to the minus 7th, so the hydrogen ion concentration is less than 1 times 10 to the minus 7th molar. And that's all there is to it, guys.